In this session, we're going to be going through the one sample t statistic. And so for the one sample t statistic, we would use this instead of the z statistic if we didn't know what the population standard deviation was. And so we might know we would know the population standard the population mean, but we wouldn't know the population standard deviation. And so to figure out what a good estimate of population standard deviation, we'd actually use the sample standard deviation. So you see here the formula. Here's our formula to get that estimated standard error of the mean. And so before we were using the population standard deviation to do that. Here what we're going to use is the sample variance. We're going to divide that by the sample size and then get the square root of that. And that'll be our estimated standard error of the mean. And so you'll see the t formula here. The numerator is the same as what we saw in the z statistic. So we're looking at the sample mean minus the population mean, just looking at the observed mean difference. And then the denominator is our estimated standard error of the mean of what we figure out here. And so I just want to remind you of this structure. We're looking at the observed difference in the numerator divided by the difference we'd expect by chance. Well, that's what this estimated standard error of the mean is calculating. It's just the difference we'd expect by chance between the sample mean and the population mean. And then one of the new things that we have here is this idea of the degrees of freedom. So the number of scores that are free to vary. The idea basically our degrees of freedom, our formula for it for one sample t statistic is just n minus 1. And I was going to go into a long description of degrees of freedom, and I think it might be best to lay off that for this. It will suffice for you to know this piece, and we can discuss the degrees of freedom at length at another time. And then this t distribution, it has more variability than the z distribution, and and the variability changes based on the sample size. So the idea is the larger the sample size, the more similar it's going to be to the normal distribution. And that makes sense because it's a better estimate of the normal distribution. So it starts to change as the sample size increases. So you see here when you have a small sample size, there's a lot of variability in the t distribution, or a lot more. And then when the sample size gets larger, it starts to look more like the normal distribution. And let's say if the sample size of the degrees of freedom were 200, then we would have something that would look just like the normal distribution. So let's work through a problem here to help you with your homework assignment. So let's say researchers wanted to conduct an experiment to look at what's the effect of alcohol consumption on the amount of dream time or REM sleep that a person has each night. And so if we know from the typical population is that the average amount of time we spend in REM sleep is 110 minutes, we can have a set of participants come in. Maybe the researchers would get them legally drunk also, that they would blow like a .08 for the breathalyzer. So obviously this is a study we're not going to conduct at Bethel, but maybe at another institution. And then they have them go to sleep, and they've got they're getting the measurements of EEG and keeping track of how much time they spend in sleep at night. And so for this particular study, there were 28 participants. The average amount of time they spent in REM sleep was 92 minutes. So we see, just compared to the population mean, there's a difference there. What we're trying to figure out is that difference larger than what we expect just by chance between the two groups. And so that's one of the things that we'll test here. And then you see here as well is that we have the sum of squares for this group. And so one of the things we're going to want based on that formula that we had there is we want to figure out what is the variance, the sample variance for this. So a reminder that formula is the sum of squares divided by n minus 1. So in our case, our sum of squares is 2187 divided by 28 minus 1. So 2187 divided by 27 gives us 81. And then if you'll remember that the standard deviation is just the square root of that, the square root of the variance, then if for the standard deviation would be 9 then, square root of 81. So as we walk through this, let's set up our hypotheses. So we'd have our null hypothesis, that the mean for the REM, for the alcohol group equals the population mean, and the alternative hypothesis then that the mean for the alcohol group does not equal the mean for the population. Okay? So just by virtue of this, how you see I've written out my hypotheses here, we have a two-tailed test. So we're saying that it could be that they're getting more REM sleep, or it could be that they're getting significantly less REM sleep. So for this, we'll set as our alpha for this equal the default of 0.05, and that we have, as we said, a two-tailed test for this. And so we would look this critical region, so you know you have Appendix B in the Johnson text, and you look back here for this t-distribution that you see, and the top row we've got the two-tailed probability, and then we have a one-tailed probability, and so we're going to have a two-tailed probability, right, because we've made a statement that it's going to be a two-tailed test. And then if you'll see here as well, that we have the probability or the alpha levels across here, and so we have two-tailed at 0.05. And then the other piece of information that we need here is the degrees of freedom. And so for us, our degrees of freedom were 27. So if I go down to 27, and I realize it's kind of hard to see here on this video, I go 27, I go across to 0.05, our cutoff is 2.052. So 2.052, and then it's two-tailed, so it's also negative 2.052. Those are our critical regions here for each side of that. Okay, then we'll go through our calculations here. So remember our T formula here, sample mean minus the population mean, divided by the standard error of the mean, which the standard error of the mean is the sample variance divided by the standard the sample size, and then we get the square root of that number. Okay, so for us in this case, our sample mean is 92 minus the population mean of 110 divided by, we figured out that variance to be 81, divided by n, the sample size of 28, and then we'll get the square root of that. So for our numerator, right, 92 minus 110 gives us negative 18 in the numerator. And then our denominator, 81 divided by 28. And then we're going to get the square root of that number, remember, so 1.70. That's the amount of difference we'd expect by chance between the two means. And so you'll notice our numerator is quite a bit larger than that. So our negative 18 divided by 1.70 is going to give us negative 10.59 as our t-statistic. And we look here, negative 10 point, that would be way out in here, certainly in the critical region. So our decision here is going to be to reject the null hypothesis. The null hypothesis said there was no difference. We reject the null hypothesis, and we say there is a significant difference. And the key here then too, in terms of explaining that significant difference, is we're saying, alcohol consumption to where it gets you at a 0.08 level of alcohol really significantly reduces the amount of time that you spend in REM sleep, or the amount of dream time that you end up spending. Now, you'll remember as well that we talked about effect sizes, the Cohen's d. So if you'll remember the formula for that, the Cohen's d was just our sample mean minus population mean. So the same as what we found up here, this negative 18 divided by, in this case, our sample standard deviation. So in our case, we have negative 18 divided by our sample standard deviation is 9. That's nice, easy math. Negative 2.0. that kind of effect size is just massive. You usually wouldn't see something like that in a lot of research studies. Basically what that's saying is it scored 2 standard deviations below the mean, that our experimental group scored 2 standard deviations below the mean. That's a really, really large difference that we see there.